The next example, example 4, it looks like we have to repeat the same substitution since we have the square root of x squared plus 4, but the reality is we don't have to do so. And sometimes we need not to lose track of simpler or easier substitution. So you don't want to jump right away to trig substitution. So instead of using the trig substitution, x equal 2 tangent theta, as we did last time, we use the substitution u equals x squared plus 4. If we do that, then you have du equals 2x dx. Since we need dx, x dx, then x dx by itself will be 1/2 du. Okay? And this becomes a rather simple exercise. The integral of x dx over the square root of x squared plus 4 will be now the integral of 1/2 du over the square root of u. And of course it will be 1/2. Square root is u to the 1/2, so we look at u to the negative 1/2 du, and the antiderivative of u to the negative 1/2 is 2 times u to the 1/2, right? We divide by 1/2, so it will multiply. So it will be 1/2 times 2 u to the 1/2 plus c, or you end up having simply the square root of u plus c, and at the end we need to bring back x, so it will be the square root of x squared plus 4 plus c. So sometimes you don't have to work hard to solve a problem like this. Tyler, do you mind closing the door? We haven't used the secant yet, so let's use the secant in our next example. Let's evaluate the integral dx divided by the radical square root of x squared minus a squared. And we let a to be a positive value. So looking back at our little table of substitution, you can see that x squared minus a squared call for the secant, okay, with the domain restriction and so forth. So as we solve it, we're going to let x be, did I put it in general? Yes, a times secant theta, and therefore dx, the derivative of the secant is secant times tangent, so dx will be a times secant theta times tangent theta d theta. Just to remember that theta can be a value greater than 0, less than, greater or equal to 0, less than pi over 2 if you're looking for positive, or if you're looking for negative, it will be greater than or equal pi, less than or 3 pi over 2. So either first quadrant or fourth quadrant. Okay. As we do the substitution, let's look at the radical, the square root of x squared minus a squared, after the substitution becomes the square root of a squared secant squared minus a squared. You factor out the a squared and you take the square root, so because a is positive you have a, and then you have secant, the square root of secant squared minus 1, and remember the identity that we wrote in our table. secant squared minus 1 is the tangent squared. That's all Pythagorean identities. All these three identities are the group of Pythagorean identities from trig. This one is cosine squared plus sine squared equals 1. This one is straight up 1 plus tangent squared equals secant squared, and so is this one rearranged. There is a third one, cotangent squared plus 1 equals cosecant squared. Anyway, so we have the tangent, so this becomes a, this is the square root of the tangent squared, so we end up having a times the tangent. And this is the radical, so now the integral of dx over the square root of x squared minus a squared can be written as the integral. Instead of the x, we have a times the secant tangent d theta, and the denominator is simply a tangent theta. So the a is reduced and the tangent is reduced, and we end up having the integral of the secant by itself, right? And this integral is one of those special integrals that we worked on yesterday. And remember the outcome of this integral, natural log of what? We talked about reviewing the notes before class, after class, and then before the next one. Obviously, many of you did not review the notes from yesterday. Secant plus the tangent. So it's a natural log of the absolute value of the secant plus the tangent plus c. So you don't have to redo this, and that's the advantage of if you have. I told you yesterday we did 6 examples. 4 of them were examples that you can use in the future rather than redo it. We evaluate the integral of the tangent, the integral of the cotangent, the integral of the secant, and the integral of the cosecant. This needs to go into the arsenal of known integrals. So, for instance, in a test or in assignment, you don't have to resolve it. You know what is the solution. The integral of the cosecant, if you remember, was the cosecant, the natural log of the absolute value of the cosecant minus the cotangent plus the constant c. Okay? What was the integral of the tangent? The natural log of the absolute value of the secant plus c. And what was the integral of the cotangent? The natural log of the sine, the natural log of the absolute value of the sine plus c. Those 4 integrals you need to know. Anyway, so this is the solution in terms of the secant and the tangent. Now we need to bring back x, and remember the substitution was x equal a secant theta, so you know that secant theta equals x over a. So we need also the tangent in our solution. To get to the tangent, we'll construct this little right triangle in the first quadrant. And the secant, the cosine is adjacent over hypotenuse, right? The secant is the reciprocal, so it will be hypotenuse over adjacent. X over a, x will be the hypotenuse, a will be the adjacent, and what is the opposite? Well, by the Pythagorean theorem, this will be the square root of x squared minus a squared. Shouldn't surprise you. I told you already one time that the missing side going to be the radical. You see it one more time. In the example before, it was the hypotenuse. This one is one of the sides. We need the tangent. The tangent is opposite. In this case, is the square root of x squared minus a squared over adjacent, which is a. And now we have everything we need. The solution to the integral, so the integral of dx over the square root of x squared minus a squared is the natural log of the absolute value. Here we have x over a plus this over a, so we can put it in common denominator. It would be x over a plus the square root of x squared minus a squared over a, like so, plus c. Questions about this exercise, or if there is a step that is not clear, before I move on to the next one, let me take your questions.